All right, welcome everyone. Thank you for joining us again on this last day of the working week. So as I mentioned, TBM cross-passage or cross-passage waterproofing in general, it really should be, is a topic that's pretty close to my heart, as most of you who know me know. I'm pretty passionate about tunnel waterproofing. It's been an area that I've been involved in for quite a few years now, decades actually. And cross-passage waterproofing is one of the most challenging areas of tunnel waterproofing. Has very complex shapes. You have heavy reinforcement. You have terminations to the TBM segments to be dealt with. A lot of detailing compressed into a very small area that needs to be addressed. And over the past 10 years, there's been a really strong engineering approach to improve outcomes. I do remember, going back to the early stages of my career, it was almost accepted that TBM cross passages couldn't be waterproof successfully. It was just too challenging, too difficult to get around the gaskets and seal to those segments. So hopefully, by the end of this presentation today, you'll see how we approach it now and how we've taken an approach that puts some science into what we do and improves the outcomes. So why do we need dry cross passages? You need it for durability of the structure, obviously, for the entire tunnel. It needs to be safe for access and egress, particularly in cross passages, because they're used for safety, for the public to move from one tunnel to the other in the time of an emergency. And they often contain critical operation equipment as well, which can corrode. So you don't want groundwater getting in and affecting that equipment. And also the treatment and disposal of groundwater is costly, so it adds to the total life cycle cost of the structure as well. And contractor's reputation becomes important when you have leaking cross passages. You have an unhappy client, I guess. So you have two types, as always, with any type of tunnel. You have drained and you have drained cross passages as well, where they limit the hydrostatic head. You have a drainage medium, as you can see in that photo, with a dimple drain, where the water can actually pass behind the concrete once it's poured and flow down into drains and be taken away. So that's one type with lower pressure. And then also you have tanked cross passages, and this is where they're fully sealed all the way around, sealed to the tunnel itself, and full hydrostatic head is able to be created above. And you could have, 40, 50, 80, 100 meters of waterhead above that you have to seal against, and this is where we use a liner to seal on that. So membrane selection, some of you who've sat in on the waterproofing basics last week will have covered some of this already, but I thought I'd just touch on the topics just briefly again for those who haven't seen it, because it really is relevant, the type of membrane you select and then the type of installation methods as well. So first, I thought I'd just quickly mention spray applied membranes. They do get used in cross passages because they're perceived to be fast to apply and they can conform to the curvature really easily. And as I said, cross passages are fairly complex structures, but they can only be applied to dry surfaces. So you can see there in that photo, that's more typical of what you would see in a cross passage. I mean, let's face it, you wouldn't build a tunnel using segmentally lined tunnel unless you had reasonably poor ground. So if you've got poor ground, when you build your cross passage, you're probably going to be dealing with tougher ground conditions than you would have normally. So the idea of trying to apply a spray applied membrane to that is always going to be a challenge. So it's difficult to apply because of the dampness, also the quality of the rock. You also can't complete pressure termination. So where that membrane meets the segments, you can get a little bit of bond there, but you're only relying on bond. And then how do you connect that membrane through to the gaskets in the TBM segments? We'll talk about that in a moment as well. So that's difficult to do. And, just controlling thickness and pinholes and other things in this type of environment is too difficult. So needless to say, I'm not a fan of using spray applied membranes in cross passages. I haven't seen many, if any, successful applications using those methods. So what we'll focus on is sheet membranes as the preferred method of waterproofing cross passages. So it's a flexible membrane. PVC is one type. There are two types we typically deal with. PVC being a softer membrane, it's a little bit more flexible, it'll conform to surfaces, usually requires lower skilled installation, relies on hand welding, mostly for the complex welds, and it's usually only suitable for drained applications rather than tanked applications. VLDPE membrane, on the other hand, it's a lot more robust VLDPE membrane. It can also be extrusion welded, and I'll talk about the different welding methods. It has the highest resistance to damage in a tunnel, which is important when you're dealing in such a confined space. It also has chemical resistance. It does require a higher level of skill from an application point of view, but it really is the membrane you need to use where you have a specification that calls for no damp patches and you're trying to resist high water pressures. So this would be the membrane you used in a tanked cross passage. So the different considerations when it comes down to selecting a membrane, you need to ask, is it tanked or drained? Does the specification have certain requirements that need to be met? Like, are there no damp patches required? Is there a complexity of shapes? Because cross passages are always in various shapes and require different types of welding. What is the termination system required and what pressure head of water are you trying to resist? And is there ground contamination? So these will determine what type of membrane you end up using. So membrane welding, just to cover it off again, as I said, we spoke about this last week. Double seam welding, this is the primary welding technique. You use this as often as you can. In cross passages, it's a little bit more difficult to use this method of welding, just because there's so much three-way curvature. This type of welding works well in straight runs, but doesn't work well in curves and short runs. It's very reliable, provides consistent results. It's all machine and computer operated. And as you can see there, you've got the two rollers which create a double weld, and then you have an air channel in between, which means it can all be quality tested afterwards, as you can see in the photos here. So you've got the little air channel in that top photo, and you can see that the channel is being air pressure tested in the other two photos. So this is why the double seam weld is so reliable, but we can't always do that everywhere. So where you can't do a double seam weld, you have to do a hand weld. And you can see in the photo on the right-hand side, all of those little black lines represent hand welds. That's been done with VLDPE, where an extrusion weld has been done over the top. So the black shows you that there's a hand weld in those locations. And as you can see in a cross passage, there's a really high density of hand welding required, which means that it becomes quite critical, and because it's so commonly applied in a cross passage. And it relies on the applicator, putting heat in, hand rolling, as you can see in those photos. So on its own, it's not so reliable, but that's all you can use in PVC type membranes. When it comes to VLDPE membranes, you have the option of doing that extrusion weld over the top. And you can see in that top photo, the black HDPE, which has been molten and put over the top of a hand weld. And that provides a double weld, a second layer of protection on that weld to make sure that it's sealed. And it's only available on a VLDPE type membrane, which is why we use VLDPE membranes in critical applications, because you've got that double welding system. Not to say that we don't use PVC, I would say it's a 50-50 choice between the two, PVC and VLDPE. You just have to be mindful of the difference when selecting the membrane for the application. So that's a little bit on membrane. Getting into actual cross passages themselves now, we can start talking about how we terminate the membrane to the TBM segments, because this is a really critical part of cross passage waterproofing. And the waterproofing membrane can be fixed in two locations. And you can see there in the diagram, it can either be fixed to the cut face, which is where you saw cut your segments to create the opening, or can be created on the rear face. And I'll talk about both those options in a little bit more detail, but both options require continuity with the TBM gaskets. So there has to be a seal between the fixing of the membrane and the gaskets in the TBM segments. So when you're talking about rear face fixing, you can see there in the diagram that's being fixed to the back face of the segments. It requires less surface preparation because the back of those segments are already smooth. They haven't been cut like the cut face. And generally sealing to the gasket, which you can just see there in purple, is a little bit less problematic. It's closer, it's easy to tie into. You can create a good connection between the two. The disadvantage with rear face fixing is that you need a bigger excavation face. So you'll see in some of the photos that I'm going to show, to be able to expose that rear face, you have to excavate out further. You have to allow a space for a drill to get in there to be able to drill those fixings. And it's actually quite a lot of extra excavation that's required to be able to create that space. So you've got the advantage of it being potentially a better seal, but you've got the disadvantage of needing more excavation space. When you look at the cut face fixing, you don't need as much excavation. You can just excavate straight up to the line of the cut. You don't need to excavate behind. Sure, you require a lot of extra surface preparation because that cut face is going to be rough. It will have defects in it. It may have the edge of the segment exposed, which means it's got dowel bar holes and other things that have to be fixed. And there's also the internal corners where the vertical and the horizontal faces meet. That become a bit of a challenge to create compression in that area, also to make sure that that area is clean and ready to accept a compression seal. What's causing more problems over the last couple of decades is that when you look at the TBM segments, the gasket is actually moving further and further to the back of the segment, to the point now where I think the gasket has moved as far back as it possibly can to the back of the segment, and it's been realised that that is the ideal position for a TBM gasket. When you go and put your compression seal ready for the membrane on, there's a gap between the two. So that'll be in the midpoint of the segment, and then you'll attach the membrane. Just lifting that membrane back up, what you can see is that it creates a discontinuity between the TBM gasket and the compression seal that you're creating. And this is one of the most challenging areas in terms of being able to achieve the waterproofing, because as you can see, the water can go in that point, go around and come out the other side. So it's really important to create that seal between the two. And that can be done in a number of different ways. It can be pre-injected into that joint with a hydrophilic resin. You can put an additional gasket in. You can put a flexible sealant between the two. And it all comes down to the amount of water pressure being resisted to determine the type of sealant, also the movement that's expected. So whether you need something to accommodate large or high movement, but this has to be engineer designed in the same way that the compression seal has to be designed, which I'll go into in some more detail as well. So just talking more about the terminations and the pressure gaskets you create, you can see there in the photo a typical compression gasket that's bolted in and fixed to the segments. So it's an engineered system, as I mentioned. The pressure that you're aiming for in the gasket has to be 2 times the maximum amount of water pressure you're trying to resist. So you have to know how much water pressure you're trying to resist before you can complete this termination. The surface must be flat and well prepared. And we use a couple of models to determine how this system is designed. We design the plate and the plate thickness, the plate width, the gasket hardness, the gasket thickness, and how much we compress that gasket to tell us how much pressure we're going to be resisting. So that's all part of the design. For a typical 80-metre design, and this has been tested on a number of cases as well as being theoretical, we've set up mock-ups and tested this for projects. But for a typical 80-metre design, you may end up with a 10-millimetre thick compression plate. So that's quite a thick plate, 100 millimetres wide, with a 12-millimetre thick gasket with a hardness of about 50 to 65 Shore. And we'll typically compress that down to about 50% of its thickness. And that's how you measure it, and you ensure that, that you've got the seal, and you've got to be able to maintain that compression between the fixings as well to achieve that negligible leakage. So it's all part of the process of design and then install and then checking to make sure that you don't get any leakage. So that's compression gaskets. We also utilise epoxy terminations in certain applications. They're typically only suitable for dry surfaces, which makes them a little bit problematic for cross passages. I don't like them for TBM cross passages simply because they don't have the flexibility needed. We all know that TBM segments will move as the pressure increases, and the epoxy won't tolerate that movement. So I would say that epoxy isn't suitable for TBM segmental line cross passages where you're going to have movement and where you have water pressure. It is faster to apply, so it can be used in certain situations, maybe where you have a drained cross passage, particularly in a mine tunnel rather than a TBM tunnel. This is how an epoxy termination looks. It's a piece of membrane which is felt back. It's bonded to epoxy, and then the membrane is welded and becomes continuous with that. So some of the other waterproofing details to be considered are anchorage. So when you need to make fixings through the membrane, you obviously don't like punching holes in your membrane. So there are systems, BA anchor is used, where you can install that into the rock. It has a sleeve around it which completely encapsulates the fixing. suitable for up to about 20 kilonewtons, and you can fix your reinforcement to it. And you can see in the photo there, all of those little circles in the photo are BA anchors, which are holding that steel reinforcement in place. And steel reinforcement can be quite dense in a cross passage because the loads are quite high around that opening. Rear guard water stop is another thing to be considered, provides internal compartmentalisation, also provides stop end protection. So where you're putting a formwork in place, it'll protect the membrane from the timber or metal formwork. Fully welded to the primary membrane. And what that does is it stops water from travelling behind the concrete, between the concrete and the membrane. So if you do end up with a leakage in one spot because someone comes along in 20 years' time and drills a hole through your concrete and straight through your membrane, then that leakage will be compartmentalised to that one area. And you can see in the photo there that what we do is we'll pick areas of high risk like a cross passage, and that's being completely isolated and compartmentalised by that black line of water stop that you can see, which is taken all the way around the cross passage, and eventually that bit along the invert will also be connected and create a complete loop all the way around the cross passage, and that stops water from travelling from one compartment to the other. We also use injection hose, and this is important in cross passages. We know that we get movement in the segments, and that can result in, even if your termination is completely perfect, there could be leaks that occur in the TBM segment gaskets themselves. So you want that ability to be able to inject that zone after you've installed it and after the pressure has come up. And the injection hose allows resins to be injected into that area without having to drill later down the track. And they're a good insurance policy for later. So you'll tend to see these used a lot around terminations and cross passages. We also need to protect the membrane once it's installed, because you'll need steel reinforcement and other activities coming in. And that can be done either by laying membrane over the surface, as you see on the two outside photos there. The middle photo, you can see a concrete blinding layer has been used. Less likely to use a blinding layer in cross passage for a few reasons. One, it's difficult to get in there. Two, it actually takes up thickness, so you'd have to excavate further. That's not always desirable in a cross passage, and typically the turnaround times are too fast. So the membrane will be installed, the reinforcement installed, and it'll all be concreted up within a matter of weeks. So there's not a lot of exposure time. You also have to consider dewatering while the membrane's being installed, particularly obviously in tanked design. Once the membrane is fully sealed up, you will need the availability to be able to draw that water from behind the membrane, the groundwater that's building up, so that pressure doesn't build up behind it. So you need to think about how that's going to be connected to your membrane and then how it will be capped off later. And there are certain designs for being able to do that. And it is often overlooked during the design stage. It's something that comes up once you're actually on site. You realise you've got a lot of groundwater to deal with, so a system needs to be implemented. But it's good to have it prepared in advance. Some of the construction considerations, things like formwork fixings are important. Quite heavy formwork around cross passages quite often has to be fixed through the membrane. How do you do that? We use things like BA anchors. We also have options for GRP dowels to be put through the membrane and sealed off. So there are ways of doing it, but it is something that needs consideration. Storage of materials afterwards. So is there a place to store my materials that are coming in to be used once the membrane's installed? You can see photo on the left, good outcome, photo on the right, pretty bad outcome. You can see the storage of materials there on that membrane really is, possibly going to cause some damage to that membrane. Fire safety, when you have lots of plastic installed in a very small confined space, certain systems have to be implemented to maintain fire safety. You don't want rolls of membrane piled in locations. You obviously want to be careful with your hot work and other things that you're doing around the membrane, and you want to have enough safety mechanisms in place if there is a fire to be able to put that out. Traffic over the membrane needs to be protected because there will be certain activities that have to happen afterwards that require access and movement of materials so that you can traffic across the top. And lots of different ways of doing that and protecting your membrane as you go, whether it's a concrete blinding layer, rubber matting, or a timber structure or something that needs to be built over the top. Steel fixing, as I mentioned, very high density reinforcement around cross passages. So it needs to be designed either through the use of lattice girders, as you can see there in the right-hand photo, some sort of mechanism for holding it in place, or the BA anchors or something along those lines. it does become a pretty big consideration in cross passages, how you fix your steel reinforcement. And then finally, sequencing of the works as well as is important. Ideally, you can get in there and install your membrane all in one go, if that can be worked in as part of the design. On the other hand, sometimes you have to go in and make 2 or 3 attempts to get the membrane done. You might be doing your invert first, your entry, your exit points, and then your crown last. Makes it a bit more complex. So sequencing of the works needs to be taken into consideration. So that's the broad overview of how we complete waterproofing in cross passages. What I have now is a sequence of photos taken from Airport Link on 2 different types of cross passage that we completed up there. One was completed using steel set openings, and this was the method that was also implemented on the Waterview project in New Zealand. And then I'll take you through the alternative option, which is the more common option of just having to cut segments. So, I mean, this is just a bunch of photos which will give you an idea of what was done. So these are the steel segments, as you can see, that were placed when the tunnel was constructed, which makes it really easy then just to open up the cross passage and start your excavation. What it also does is helps us with installation of the compression steel. As you can see there, we're using the steel segments. We've used a stud welder and we're welding the fixings directly to the segment. We're able to fix our compression seal directly to that. Makes it a lot easier, much smoother surface to deal with, much easier to connect to that segment gasket as well. So just flicking through the photos, you can see the compression gasket going into place and all of the fixings. The access over the top, obviously doing the crown first, coming back to do the invert last. Access into the cross passage becomes important. You can see the injection hoses around that compression seal. The protection layer going in and the steel reinforcement being laid. Concreting works about to start. Concreting the internal. And then there's your finished product with the steel sets and obviously the concrete encasement of those the steel sets as well. Moving over to the cut segment openings, you can see there the concrete segments have been saw cut across the top, and then the hole segments have been removed to create the vertical part of the opening. You can see there that there's a lot to deal with, particularly in that right-hand photo, in terms of being able to prepare that surface ready for a compression seal. There are openings in the concrete segment that need to be sealed across. You've got shotcrete across the surface, and also that top internal corner to be dealt with. And there's a better photo of that top internal corner, and that's what I was talking about earlier, needing to repair that. This is a cut face fixed membrane. So you can see there that the excavation actually comes right up to the segment. It doesn't have to go behind those segments to create extra space, and you can see that in these photos as well. Coming back to that other photo that I mentioned, it would have been difficult to apply a spray membrane in this circumstance, but you can see pushing ahead with a sheet membrane by dewatering as best we can, but still able to install that membrane effectively. You can see a lot of the welding detail that goes into this, a lot of three-way curvature to be dealt with. So in this case, it was a PVC membrane that was used. You can see there it being installed, and on that right-hand photo, the lobster backing, and the middle photo as well, just to be able to deal with that three-way curvature. And the compression seal being finished off. I'm ready for concreting, reinforcement to be installed. A bit more of the injection hose. These presentations will be available to download, so you'll be able to see these photos a little bit more closely. And then, of course, at the end there, I mean, this is what you want a cross passage to look like, nice and dry. This cross passage was probably 40 or 50 metres below the water table, but no sign of leakage. And if you've done your work properly, this is what you hope to end up with. So just in summary, cross-passage waterproofing is a really complex area of tunnel underground waterproofing. There's a lot of detailing to be completed in a very small space, so you have a very high concentration of complex activities. The engineered terminations are probably the most challenging part of that, but you can design those so that you achieve a seal, and you can build them so that they can resist high pressure water, and you can achieve those dry cross passages. So thank you for joining us today. I welcome any questions you might have, either by taking yourself off mute or otherwise dropping a question into the chat there. I also have just popped my email address on, so if any of you would like to send me an email afterwards, more than welcome to do so. Happy to ask questions. Really enjoyed the last couple of weeks. We hope that you have too, and thank you again.